So there's a very handy method that we have to do beam deflection problems by integration. So, and what it kind of centers around is the idea that when we do beam deflection problems by integration, kind of in the normal way, the way we covered it last time, one of the things that we have to do is take the beam and split it up into little segments based on our loading configuration, right? So any place in the loading configuration where we have a discontinuity, those become places where we are required to essentially split the beam up at those locations and essentially treat each of the little segments with its own, let's say, bending moment function that we will then begin to integrate and all that. And that can be a little bit cumbersome, right? So every place that you split up the beam into multiple segments, that becomes another place where you are likely to have to do continuity equations, and that becomes probably a couple of more constants that you're going to have to solve for using an ever larger system of equations depending on how many of those divisions that you have to do in the beam. So this is an example that I've got up here. If you'll notice, how many segments would we have to split this example that I'm showing up here at the top of the screen? How many segments would that have to be? Okay, so we would have to first do one that would go from the left support to where the moment is, right? That would have one bending moment function that would apply within that segment. Where else would we have to, then from the moment where? To the, right, to the beginning of the distributed load that we have right here. How far can we go from there? Yeah, you can really only go up to the support because that support actually represents a concentrated load. And so that's another discontinuity in the loading function, or kind of the loading scenario on the beam. And then from there, we probably could go from there to the end of the beam. But just for this, not even that complicated of a loading scenario, we would have to split this up into 1, 2, 3, 4 different sort of segments in order to do this, which means every one of those splits that we made, there would probably be 2 sort of constants that would sort of get added into our overall system, because each one of those places we would be able to use continuity equations for slope and deflection at each of those locations. But you can see that very quickly you can start having to have large systems of equations that you might have to solve to come up with all those constants of integration using the ordinary beam deflection method using integration, okay? So here's basically what I'm trying to say, is that if there was some kind of way that we could create functions that were actually, that we would actually be able to integrate across these load discontinuities, then it would very much help us out, right? And so I'm going to show you today is a way that we can do that, and it involves using these functions that in some places are referred to as Macaulay functions, okay? In most of these textbooks where you learn mechanics of materials, they just call this the discontinuity function method that I'm about to show you. So first, let's look real quick at this Macaulay function. This is how it's defined, and this is literally just, let's just say this is how we're going to define it, okay? What we're going to define it as is that we have a variable x that describes a position along the length of the beam, and then a variable a that describes a particular position along the beam. Okay, so that's all you need to know at first, is that x is sort of describing any location along the beam, and a is describing one particular location on the beam. So a is less of a variable kind of and more of a constant. Okay, and if we then use these little sort of angular brackets, that denotes that we're talking about a Macaulay function. Okay, and so then we take that to this n, and here's how we define that. For any x value that is less than a, we're literally going to define this function as just being 0. In other words, it doesn't really exist prior to specific location A. Okay? Then, for any x values that are greater than or equal to A, this function just becomes itself, right? Basically x minus a to the n. So think of it as long as x is greater than or equal to a, then this just becomes like it would be with just plain old parentheses, right? This is how we're defining this function. Now, what's nice about this particular function, and I won't spend time trying to prove it right now, is that if we integrate this function, right, because this function itself has a discontinuity in it, right? It's different you know, if we're to the left of A than if we're to the right of A. See that? Like it's got a discontinuity in it. But when we integrate this function, it is possible for us to do that. All we have to do is just do the same type of integration step that we would if this was just a plain x minus a with parentheses to the n. Okay? As long as n is greater than or equal to 0, you would integrate this kind of with the exact same steps that you would do to integrate it if it was just x minus a in parentheses raised to the n. That means you increase the exponent by 1, divide by the new exponent, and add a constant whenever we do this integration. Okay? Now, let me show you what this kind of becomes for a bunch of our different loading cases. Okay? This is, you know, this is sort of something you just sort of have to, I guess, either have this table or memorize a few things. But let me show you this. So for a concentrated moment, okay? Let me actually start with the most direct definition of what a concentrated moment would become, and I'm going to cruise all the way to the right side of this table. A moment function that you would describe this would basically be whatever that moment value was, m sub 0, with the Macaulay function of x minus a to the 0. Okay? And anyway, if you wanted to figure out what this was as a shear function or as a load function, you could basically back up from there, and you can see that these other definitions are going to be present for what the function, the proper function would be for the loading function or for the shearing function. And I won't necessarily step through all of these other than just to note, I want you to notice here, for each of these first 3 loads, we're talking about a concentrated moment, a concentrated force, and then a distributed load. Notice that for each of these, the version of it that is to the 0th power is the one that describes that kind of load, right? So if we're talking about a load function, distributed load function, then the Macaulay function that we used for that goes to the 0th power, right? If we're talking about a concentrated force, which is very related to what the shear function is going to be, that one is to the 0th power in that case. And then for the concentrated moment, that one is to the 0th power in that case. Okay? But if you're worried about it, I am not actually going to deprive you of this table whenever you get ready to do a test. This is going to be one of the things that I provide for you in the test, so you don't have to spend a lot of time trying to memorize the stuff that's in this table. I do want to show you something, though, that you might already be looking at this table and going, why does it start to become different as far as, you know, the definition of these things? So you'll notice that with the distributed load function, notice there that our n value is 0 in that case. See that? Okay. So if we look at our definition of what this integration would be, this totally makes sense, because what we have to do here is we would have to take the original function, increase the exponent by 1, and divide by the new exponent. Since we're increasing 0 to 1, the new exponent becomes 1. So we divide by 1, and so there's not a new exponent that shows up here. See that? Because we're really just dividing by 1. Okay? You'll also notice that we are not adding a constant as we do that integration right there. We'll talk about that just a little bit more in just a second. But for right now, just notice that going from here to here, even though we hypothetically could apply this function, or this definition of how to do an integral, we're still not coming up with a plus c when we go from the load function to the shear function, which, you know, integrating that is how you'd get from the load function to the shear function. Does that make sense? We also don't add a constant. We go from the shear function to the moment function. Okay? So right now, just note that. I might talk about that a little bit more here in a few minutes. But you'll notice here, going from the shear function to the moment function, what do we have to do there? We did actually divide by the new exponent when we did that integration, going from the shear function up to the moment function, but still no constant. Okay? Now let me show you this. We have one more example of these discontinuity functions that are applied to different kinds of loading. This last one is applied to a triangular load, right? A load that has this constant slope to it with regard to how it is defined. And that slope is actually given with the variable m in this figure right here. Okay, notice how this one starts with a power of 1 on these Macaulay functions. Okay, and Then from there, it increases by 1 and does exactly what you'd expect. Divide by the new exponent, you get that factor of 2 in the denominator. Again, you would do exactly what you'd expect, increase that exponent by another 1. The 3 that you now have gets multiplied by the 2 that you already had in the denominator. You end up with a factor of 6. Okay? Here's what I want to show you. There's actually some special rules if you end up with negative powers on these Macaulay functions. Okay? So here's what I want to show you. Those special rules actually apply to special loading cases. So, and this is what I want to say about these, right? The integration rules for, it's called singularity cases. Technically, if you actually think about either one of these kinds of loads, P or M, where P is a concentrated load and M is a concentrated moment, are these actually possible in the real world? Okay, so think about what this would actually mean to have a load applied over 0 length, right? That's what a concentrated load actually is. It's a load that gets applied in exactly one location. Now think about that, what that would be in terms of the idea of stress. So if you have a particular amount of load that you're applying over 0 length, how much area would that be that you're applying that load distributed over? 0, which means that if you really had that, you would actually have infinite stress, right? No material we have actually can carry infinite stress. So either of these two loading types are somewhat of, they're kind of fictitious ideas, but they are useful fictitious ideas, and here's why. So there are enough loading scenarios that exist in the real world that are close enough to being kind of like this scenario. Imagine it this way, right? If you apply a load not over 0 length, but over a very short length, they're almost the same in terms of how they affect the rest of the beam, whether it be 0 or whether it be very short, right? And so it's useful for us to define what these are, but that's the reason that we use this word singularity with regard to these cases. Singularities are kind of these things that don't really exist in some way, right? They're kind of almost, you have to think about these as just ideas. Same thing, by the way, with the bending moment, right? If you have, or excuse me, a concentrated moment. With a concentrated moment, it is applied at one location, and that is actually impossible to do, because in the real world, the way you would accomplish a concentrated moment might be, let's say, to like weld a shaft to the side of a beam, and that shaft would be ready to apply some kind of a twisting action to the beam. We think of that as being a point, but really, you do have to have an area over which that shaft actually connects to the beam, and that's actually what's causing these multiple forces really applied over an area to create a twisting action. I don't want to beat that to death, but at least I wanted to describe what we mean by singularities. It's essentially loading conditions that can't actually exist, but they still are useful for us to be able to model certain things as though they did exist. Does that make sense? Okay, and you'll notice here that these are the special integration rules for these kinds of loads. If you're talking about a concentrated load, that is just some kind of force, P, that you're applying right there, taken to the, or multiplied by the Macaulay function taken to the -1. And when you have this, to do this integration, you literally, you'll notice here when you do this integration, you are not dividing by a new exponent, and you are not applying a constant to it. So these are kind of special rules for these Macaulay functions, and that applies kind of the same way to the bending moment, other than the fact that for the concentrated moment, you'll notice that it starts out with an exponent to the -2, and so for both of these integrations, from -2 to -1, and then from -1 to 0, neither one of these cases will you apply the rule of dividing by the new exponent or adding a constant. So here's kind of the two things that I'll mention about this. If you really examine this table, you will figure out that there are a couple of patterns that allow you to understand this table by just understanding the definition of a Macaulay function as well as its integral, and then these two special cases, okay? These are the rules that essentially allow you to develop a table like the one that I'm showing you right here. So if you were out in the wild, let's say, it wouldn't be that hard. You wouldn't have to know that many things to be able to reconstruct this table. But I already gave you some assurances. I'm not going to take the table away from you for any kind of high stakes events that we might be having with regard to the content of the course. Okay? Now, at this point, you're probably going, that's all fine. I still don't really know how to do one of these problems or what to do with this stuff. And I think the best way to show that is by doing an example. So we're going to get into this example here. It says here, use discontinuity functions to express an elastic curve for this beam. It says, then find the deflection of the beam at points B and C. That's basically to give you a little bit of practice of using one of these elastic curves expressed in terms of discontinuity functions. They can still be used to determine what your deflection is going to be at any point. So I'm going to show you a couple of points where we can figure that out. Okay? Before I really get started with this, let me just mention a couple other things. We know what the EI, the product of the elastic modulus and the second moment of area, let's say we know what that is for this beam. We'll say it's 10,000 kilonewton meters squared. Also, notice that we have a sloping triangular load being applied from point A to B. It peaks out here at the very top at 18 kilonewtons per meter, right? So that's essentially the value right there at the peak point for this distributed load. Additionally, we have a concentrated moment being applied at location C. Just like you would with generally, many other of these kinds of problems, one of the very first things that would be very helpful for us to have are reactions at the supports, okay? And I don't want to spend too much time going over an example of how to find reactions at the supports, so let me just flip right over here and say this is definitely a process that y'all could probably do in your sleep, hopefully by now. What you do is you lump the triangular load into a concentrated load. That concentrated load is going to exist 2/3 of the way from the point to the flat of the triangular area that is essentially defining that load. The amount of load is the area under that triangle shape, right? So to get that, you do 1/2 base times height. After that, we do a sum of moments around point A. When we solve that for R sub D, we get 4 kilonewtons as the reaction at location D. Once we know that, we can then do a sum of forces in the Y, and we can get what the reaction is at location A, right? So we get 23 kilonewtons at location A and 4 kilonewtons at location D. Hopefully I didn't go over that too quickly, but again, I think at this point, most of y'all can do that kind of work in your sleep. So hopefully that's good enough. So let me just go ahead and make note over here that now that I've set all these up, we have 4 kilonewtons of reaction at location D, and I'm going to have, was it 23, I think, kilonewtons of reaction at location A, okay? Now we have to get into this actual problem. So the way this works is that those loading scenarios that were given in this table up here, let me scroll up there real quick. These loading scenarios that were given in this table give us a way that we can create functions that are easy for us to integrate even across discontinuities. So that's the good part, that's the good news. The slightly less good news is that these are the only ones that we really sort of have at our disposal. These are the things that we know, okay? And that means that for our given load scenario, we have to be able to construct that load scenario based on some combination of these load scenarios that are given in the table, okay? And let me mention another thing here too. You'll notice that in the picture for this table, it shows the beam kind of cut off at some location, and it implies, especially on this distributed load as well as on the triangular distributed load, it implies that those continue on past the location where I stopped showing the beam. Here's the implication of what it's saying. What we're saying is that the kind of the effect of the load continues on all the way to the far right end of the beam. So that applies to all 4 of these, right? So, and for the last 2 of them, that means the load itself also continues from the starting point at location A, right? Location coordinate A. It continues from there all the way to the right end of the beam. So that's what we're implying with each one of these load scenarios that I have here in the table. When I look at this problem, here's my question. Let's specifically look at the triangular distributed load. Okay? Does that triangular distributed load extend all the way to the right end of the beam? It doesn't, does it? So that means that this triangular load is not something that I can immediately express without doing something else. I can't immediately express it using the rules that were in the table just yet. Okay? So here's what I need to do. I need to use perhaps multiple items that are in that table to still come up with a way to construct this load. Okay? So here's, let me sketch the beam as I am going to start dealing with it. Okay? So let me say here's the beam. Let me also put on my reactions that I was talking about earlier, right? So this is going to be 23 kilonewtons of reaction right here. This is 4 kilonewtons of reaction right here. We still have our 14 kilonewton meters. That doesn't really change, so I'll put that on here right here, 14 kilonewton meters. And then over here is where I'm going to start showing you how we can construct our distributed load that is given in this situation. And here's how I'm going to look at it, okay? I'm going to look at it as, what if I had a distributed load like the one that's given that did extend all the way to the right end of the beam, right? I'm saying that's what the table allows us to model. So let's go ahead and make it that way at first, right? So say here is our overall triangular distributed load, okay? If we were to have to model it like something in the table. Problem is, this isn't actually what we have, right? We have this triangular load stops at point B. Well, what would I have to do to turn this triangle that I just drew into the one it really is? Okay? I'd have to subtract a couple things, right? So let me say if I had a downward load that essentially I need to subtract off. Let me say it this way. I need to subtract off a chunk of stuff that is described with that trapezoid, I guess is the right word for that shape, right? I have to subtract that. I have to get rid of that part of it. How do I construct a trapezoid out of the options that I have in the table? Okay? A trapezoid can be made with a rectangular piece and a triangular piece, right? So here's what I'm going to do. I'm going to take and show that, you know, on this particular case, let me just remind us, this point right here was our 18 kilonewton per meter. That was that point right there. Okay, and it existed at a location of 3 meters relative to the left end, just to kind of keep those things in mind. And I'm going to say that one of the things we can do is if we have a downward rectangle that's shown right here, I basically need to, you know, I need to subtract that off, so I need to show this as an upward distributed load, right? To subtract that chunk of it off. And then I need to subtract another little piece of it off as well, and that would be this chunk up here. And since this chunk with the original red load was pointing downward and I need to get rid of it, it means in this case I need to point back upwards. So essentially what I'm saying is if I take the red case and add to it the blue case and add to that the purple case that I've drawn right here, it leaves me with my original case because it has subtracted off all the stuff to the right of point B. All right, so now that I've done all that, let me go back and tell you this as well. We have a couple of options about how to use the information that's in this table. One of the options is we can go all the way back to the load function itself that is appropriate for any of the types of loads that we have on our beam. Okay? In other words, we can write a W function in terms of X, and if we do that, we can take that W function, integrate it once to get V, integrate it again to get M, integrate it again, you know, throw the EI in there, and integrate it again to get slope, and then integrate that again and get deflection. That's one way we can do it. We can start all the way from the distributed load function and integrate, you know, what is it, 4 times to go all the way to the deflection function. That is certainly an option. But you might remember that when we were doing our plane integration method that we did last time, where did we often start there? With a bending moment function, right? Because they give you this nice little table, we also have the option of starting with a bending moment function and only having to integrate twice. The interesting thing is, though, that it doesn't matter very much which of these 2 options you choose because you don't have to split the beam up into multiple segments. That's the whole power of doing this method. And you don't you know, and it's really not that hard to do these integrations, I guess I'll say. Okay, so here's what I want to show you. I'm going to do it by starting with the moment function first. That's the first way I'm going to show you this, okay? So let me try to write this moment function and do the, we need to basically write this for each of the types of loads that are applied to this beam. So what's our first one? I write my moment function over here. A concentrated load of 23 kilonewtons at the very far left end. Since it's at the very far left end, first of all, which of these entries in this table does that one get represented with? The second one, right? And what A location is that force applied at? 0, right? Because this is the load that is applied at the far left end. And we are trying to get this moment function. So that means I'm going to take whatever that value is, 23 kilonewtons, and multiply by this x minus a, where a is actually 0. So 23 kilonewtons. Now, let me do this real quick. I'll do x minus 0, and then what was this raised to? To the first power. All right, let's go back and remember what's the definition of our Macaulay function. We have this x minus a raised to the n, right? What does this actually mean? It means for any x's that are greater than or equal to a, it's just equal to x minus a to the n. Let me ask you this. Do we have any beam for this first load that I just wrote? Do we have any portion of the beam that does not fit the second part of that Macaulay function? In other words, it says as long as you are greater than or equal to a, for us a is 0, then the form of it that's just x minus a to the power, that's the form of it, right? So for us, do we have any beam to the left of 0? No. And for that reason, you can do a couple of things with this. I could write it this way, but also I'm just going to show you here, this is equivalent to just saying this is times x. Because the minus 0, right, that means nothing, and there's no part of it that would actually be appropriate to model with the first element of the Macaulay function. Does that make sense? None of it would apply that would be in that x less than a condition of the Macaulay function. So that's essentially what I've got for that first load. The next one I'm going to model is the 18 kilonewton per meter, right? The little triangular load here that is 18 kilonewton per meter at an x coordinate of 3 meters. So let's go back up and figure out which of these cases would deal with that properly. It would be this last one here, right? What do I need to know if I'm trying to get my moment function? What's m? Slope, and it's specifically talking about the slope of the curve that describes this distributed load, right? For our problem, how do we determine what that slope is? We go over here, slope, m, 18 kilonewtons per meter, divided by 3 meters, right? Slope is rise over run. Our rise over 3 meters is 18 kilonewtons per meter. So if we do 18 kilonewtons per meter divided by 3 meters, it gives us this slope m. And so that basically is 6 kilonewtons per meter squared. With me? Okay. So 6 kilonewtons per meter squared is m. Let's go back up and look up the rest of the form of this thing. We need to take that value, 6 kilonewtons per meter squared, multiply it by this Macaulay function, x minus a. What's a for us? How do they define a in the picture here? It's where does it start? Where is it 0, basically, right? And it starts for us at x equals 0 for this problem, right? So I'm just going to put in here m, right? 6 kilonewtons per square meter. Again, because we don't have any material that is to the left of this point, I can still just take this and say this is going to be x, and it's going to be raised to the third, right, over 6. Now, one other thing I want to check on here. Go back up and look at the table. What direction were the arrows in this distributed load? Up. And this was the outcome with those arrows up. What is it for our problem? Down. So what do I need to do? Just negate it. So in other words, instead of adding this, I'm going to be subtracting it. And that subtraction is there literally because the arrows go the opposite direction of what they are shown as in the table. Okay? All right. So now, are we done? We're not quite done. What else do we need to do? Okay? I do have a concentrated moment. Tell you what, before I deal with the concentrated moment, let me deal with the rest of these distributed loads, because I also added this blue one and the purple one to take care of the fact that it doesn't continue on past B. So let's do the blue one real quick. What would that one be represented by? Case 3 here in the table, right? And for that one, the arrows are pointing up, and for us, the arrows are pointing up because they're counteracting the ones that were pointing down. So I am going to put this in as adding whatever that distributed load value is times the Macaulay function x minus a to the second, all that divided by 2. Here's what that means, right? We're going to add on, what's my W going to be? 18 kilonewtons per meter, because what I'm doing is that's the height of that blue rectangle, right? Because that's what the height was. Essentially, that's where kind of this blue rectangle would start right here, right? Pointing back up. It's not on that form of it, but anyway. This multiplied by what? It'll be multiplied by, excuse me, I need to do the Macaulay function here, so I need those pointy brackets like this, x minus 3 meters, okay? And if you go back up here, this would be raised to the second power, that divided by 2. What else? Now let me take care of this purple piece, which is another triangular distributed load. To describe that one, it's going to have the same form as I had for this one with the 6 kilonewtons per meter squared initially. It's going to have the same form with one little difference, right? So I'll still have the same slope, 6 kilonewtons per meter squared. It'll still be over 6. Is it plus or minus? Okay, notice this one, those arrows are pointing up, which matches what it is in the table, right? And that tells me this should actually be plus. And then what about my, my brackets inside of the brackets here? Right, x minus 3 meters, because that's actually where this distributed load starts, right? That's where that one would start at 0. Because essentially what we're modeling is something that is this this triangular piece. Imagine that slid down and applied directly to the beam, okay? And then that would be raised to what power? Third power, right? Because we're basically applying this form right over here. So raised to the third power. Okay, so those 3 terms we just put in there, essentially those 3 terms together model the triangular load that we were actually given stopping at point B. Takes those 3 terms to model that. Does that make sense? All right, now what? Someone mentioned the concentrated moment, so let's go ahead and put that one in there. What was the M function for a concentrated moment? X minus a to the 0, right? M naught times x minus a to the 0. So that moment was 14 kilonewton meters. The Macaulay function would be x minus what? That's 8, because it's 8 meters from the left to where that is located. So 8 meters. And then that gets raised to the 0, right? Let's look at the sign of this, because I just wrote that in there. This is a counterclockwise moment. What direction was taken positive in the table? Clockwise. So I need to apply this with a minus sign here, because it's opposite the direction that was in the table, right? Promise this won't be this tedious for too long, but I'm trying to make sure I explain every step as we go. All right. We've done almost all the loads applied to the beam. Are there any others we should be thinking about? We do have a reaction at, we did a reaction at A, we have a reaction at D, right? If we were to do that reaction, what would the form be? I'll tell you what, I'm going to even do this in a slightly different color to kind of indicate we might not even need to keep it. Foreshadowing, okay? But what would the form be? First of all, 4 kilonewtons is up, so I'd do plus 4 kilonewtons. That matches the direction it was in the table. So plus 4 kilonewtons multiplied by what? X minus 10 meters, okay? Raised to the first, right? All right, let me ask you this. How, again, remember our definition of our Macaulay function. How much of my beam would fit into the second portion of the Macaulay function? None of it, right? My A value for that last load I just did was 10 meters. I run out of beam at 10 meters. So other than maybe right at equal to 10 meters, this moment is not in the game. It's not doing anything. So let's think about that one point of what about x equals 10 meters, because that would technically fall under this case right here. Okay, so let's say it does that. Now we need to integrate. We're going to be integrating that across the length of the beam. How much length do we integrate it over? 0. So even though you might have one particular value right there, one particular physical location where the moment is not, I guess, 0 according to the Macaulay function, it still doesn't matter as you're integrating your moment function because you have 0 length to integrate that effect over. Yeah.
Could we also say that?
He says if it was right at 10, then x would be equal to 10. 10 minus 10 would be 0. That makes that 0. So another good reason why it wouldn't have any effect even in that case. Yes. So his question was, what if the roller, what if this problem had not been the problem I gave you and instead had more beam going past here? In that case, then you would have length that you would need to integrate over, and this load would begin to play. But since you're at the end of the beam, there's no length for it to actually have any effect. Okay? So for that reason, and just in the interest of simplicity, I'm going to take that term that I wrote and eliminate it, right? Because it's not actually going to have an effect. It's just going to be extra baggage to carry along that won't, be useful for anything anyway. Yes. His question was, would that apply to anything that's applied at the very end of the beam? And if you're using this technique always assumes you're going from left to right. Any effects that show up literally at the right end of the beam won't have an effect using this method. Okay? Because there's no length over which for it to have an effect. So, all right. This becomes my moment function. What would I do with the moment function? All right. Now that I have a function written, I can go to slope, right, by first of all dividing this whole function by what? EI. So let me go ahead and do that. Run through this whole thing. Every term you divide by EI. And again, I gave you what EI is for this problem. That would often be a given value generally for most of the problems that we would work in here. And then we do what? We integrate it. And so what does this become if I integrate it once? Slope. And you'll notice here that because we use this technique, I don't need to split the domain up. I don't need to split the length of the beam up into multiple segments. I literally just integrate this function. So what would that first term be when I integrate it? 23 kilonewtons, x squared. Okay, we're going to divide by the new exponent too, right? So this is divided by 2EI. Okay, what about my next one? I guess those 6's cancel out, right? So this would basically just be, I'll keep the units in there, kilonewton per meter squared, x to the 4th, divided by the new exponent, 4, keep my EI in there as well. Then what? Plus 18, okay, I guess 18 divided by 2 gives me 9 kilonewtons per meter. Here we have x minus 3 meters. What do I do with my exponent of that? Increase it by 1, divide by the new exponent, right? So that gives me 3 EI. What about my next term? The 6 is there, divide out again, right? So we'd have kilonewton per meter squared as the unit. Here we'd have x minus 3 meters. That is going to be raised by 1, right? The power of it's going to be raised by 1. Divide by the new exponent. That gives me 4 EI down here, okay? Am I doing everything good so far? You have to check me. I might make mistakes, all right? Then what? Minus, okay, here I'm going to have 14 kilonewton meters over EI, okay? Here I'm going to increase this exponent by 1, x minus 8 meters. Increase that exponent by 1, divide by the new exponent since it's 1. All right, and remember EI is known. I'm just, for shorthand's sake, I'm just continuing to write it as EI. Yes? So his question was the x minus 8 to the 0, would this not just be 1? Okay? Even if it is 1, we have to leave it in here like this so that we can do this integration. Okay? The answer to that is it very well might be 1, right? in this case. But we want to leave it in here like this so that we can do this integration. His point why he's saying that is that anything raised to the 0th power is 1. Okay? All right. What do we need to do now? Okay. Yes. I heard someone say what? Plus C. Okay? Just because we're using this method, it does not free us up to not do our constant of integration whenever we integrate. So we're going to have this C1 in this case as well, which brings up a good question. Is there a way that I have at this point to try to solve for C1 given any kind of information that we had, boundary conditions, right? Any kind of boundary conditions that we had in our original case, right? What would we need to be able to like introduce information to find C1 at this stage? We need a place where we know the slope already. And in this particular problem, it's not, nowhere on this problem is it constrained from rotation. So we don't have any spots where we preemptively know the slope. And for that reason, we have to just leave this C1 in here as a constant for now. Okay? So then we go to our next step, which is what? Okay, the deflection equation. So for the deflection equation, we have y of x. Okay? What we're going to do is, again, just run through this. Here we'll have 23 kilonewtons. This becomes x cubed over, divide by the new exponent there. That gives me 6ei. Then what? Minus, here we're going to increase this exponent by 1. So again, units of kilonewton per square meter. We're going to take this x, increase that exponent by 1, and divide by the new exponent. What's that give me down here? 20 ei. Okay. Here we'll notice that 9 divided by 3 just gives me 9. Or excuse me, 9 by 3 gives me 3. Hopefully that's not the math that's happening. But anyway, 9 divided by 3 gives me 3. So that gives me 3 kilonewtons per meter. Here I'm going to have x minus 3 meters. What do I do with the power? Increase it by 1, right? I just got rid of the 3 in the denominator, so the only thing I have left in the denominator as far as a constant goes is a 4 ei. Next term is going to be kilonewtons per square meter. Here I will have x minus 3 meters raised to the 4th power. Excuse me, what am I doing with the power? Adding 1 to it. So this is raised to the 5th power. This gets divided by what? 20 ei. And some of you may have noticed this, that I left off the plus sign when I did that term on the slope equation up there. I won't do that on this one. It's plus because it was plus on the original moment equation. All right, then what? Minus 14 kilonewton meters over. Here I'm going to raise this exponent by 1 again. It gives me 2 ei down here, x minus 8 meters. Now to the second plus C1 x, right? Because this is C1 times x to the 0, right? So I'm increasing the exponent of that by 1. This is now C1 x, all right? Since that new exponent is 1, divide by that. Again, dividing by 1 doesn't do anything. What else do I need on this expression? C2. Plus C2. Okay? Now we have an expression where we can start to think about trying to apply boundary conditions. So where's one boundary condition that we have? At x equals 0, deflection is equal to 0, right? So essentially what that says is I can take this expression that I used right here, right? We have a function that looks like this, right? That at an x value of 0, what do we do everywhere we have an x? We plug in a 0, right? So there'll be a 0 here, a 0 here, a 0 here, 0 here, 0 here, and 0 here. Okay? Now for some of these, that makes it very obvious what we do, right? What do we do for that first one? That one's obvious. This one's obvious. What about this next one? 0 minus 3 meters would give you what? Negative 3 meters, okay? Which if this was just ordinary parentheses, 3 meters raised to the 4th would not be 0. But this is not just ordinary parentheses. These are the brackets that represent that this is a Macaulay function, right? And since it's a Macaulay function, we need to go and look at the definition. Anytime x is less than a, what does this expression What is it actually defined as? 0. So that tells me because of that definition of the Macaulay function, this is also 0. And that means this is 0 as well. Right? And that's because the x value I'm evaluating is less than the a value that's in the brackets. Okay? What about this one? 0 minus 8. Same thing again, right? The x value is less than the a value, right? And that means this one's also going to be 0. Since this is 0, this term is 0. And with all of this stuff put in here, what do we conclude about C2? We conclude that C2 is 0. We have a similar kind of task that we need to do here, where we plug in our other boundary condition. Okay? Our other boundary condition occurs at an x location of 10 meters. Right? At 10 meters, we know that at that location there can't be any deflection because it's being supported with a roller. Right? So for this one, we are going to plug in 10 meters. Right? So everywhere we had this, we're going to plug in 10 meters. Okay? And one of the other things you may notice as I wrote this expression out is I did away with all my Macaulay function brackets. Right? Why did I do that? Since I'm taking my x coordinate at the right end of the beam, it's always going to be greater than any of my a positions that are described with my a values. Right? Does that make sense? So that means that all of these just take the form that they would with just parentheses as opposed to the Macaulay brackets, right? So anyway, this equation is not something that you'll be able to, I would say, just quickly do in your head or anything like that. But if you believe me, I will tell you that I calculated all of this, and I got that C1, because this equation set equal to 0, that allows you to calculate for C1. C1 solves out to be negative 0.0144643. And let's take just a moment and say, should that number have any units associated with it? No, because, look at the context of this equation, right? We're going to want the outcome to be some kind of length, and C1 is already multiplied by a length, so it better just be a constant with no units associated with it. Okay? All right, now that I have all of that stuff, what does my final equation of my elastic curve become? All we got to do is rewrite, right? You might remember we had this version of it up here. You rewrite this version now that you know C1 and C2. You rewrite that with C1 and C2 in place. This is my equation of my elastic curve. Okay? Expressed using what kind of math technique? Yeah, Macaulay functions, right? Notice I didn't try to take this final outcome and express it using more standard sort of regular parentheses and all that kind of stuff. And I didn't try to do it with, like a piecewise function and all that kind of stuff. The Macaulay functions are actually handling all of that piecewise stuff that you would otherwise have to do. Okay? How is that? Well, you might say any x that you pick, certain ones of these functions will turn themselves off if x is a particular value, right? Take an example, right? Let's say I pick an x value of 5 meters, and I want to figure out what this deflection is at 5 meters. What would I have to do? Plug 5 meters into everywhere you have an x, and that would leave all of these terms functioning except what? Right? This one where it would be 5 meters minus 8 meters, right? The x value I'm plugging in there is less than the a value of 8 meters, so that term would turn itself off. Does that make sense? All right, let's do a couple of more detailed examples essentially doing exactly that. So let's find what the deflection would be at point B using this function right here. Okay, here's what that would look like. So at point B, what x coordinate am I actually working on? Okay, you can go back to the original picture. Point B is at an x coordinate of 3 meters. So I need to plug in 3 meters here, and anywhere else there's an x, right? So here, 3 meters, here, 3 meters, so on and so forth. Here, 3 meters, that's kind of interesting. Here, 3 meters. and here 3 meters, and here 3 meters. Okay? Now, what happens for a couple of these terms? Right? 3 meters minus 3 meters, that's just 0, right? So no problem there. 3 meters minus 3 meters, that's also equal to 0. What about this term with the 3 meters minus 8 meters? It's 0, but for a different reason, right? This one is 0 because we go back to the definition of our Macaulay function, and what happens there, if that x value is less than 8, we're in this first case, right, as opposed to the second case of the definition of the Macaulay function. So that piece becomes 0, and it means that we're left with only the pieces that did not become 0, which essentially are the first 2 terms and the last term. All right? And again, those aren't necessarily, things you can just do in your head, but if you trust me, I will represent to you that y at 3 meters became negative 0.03426 meters for that deflection. Now let me show you here that this may change if we move to another point. It said also evaluate this at point C. So let me do the same type of thing again. We'll take this expression. This time we'll plug in 8 meters. So the x that I have right there, 8 meters is where point C is located, right? So everywhere I've got an x, we plug in 8 meters. 8 meters, 8 meters. Here I've got 8 meters. Here I've got 8 meters. And here I have 8 meters. Right? Now notice here in my first case where I did my 3 meters, I had these two terms. The 3 meter minus 3 meter gave me 0 meters. But notice here on this one, 8 meters minus 3 meters, that's not 0. So these terms do not become 0 when we're evaluating it at 8 meters or at point C. Okay? What about this term right here? Because it's 8 meters minus 8 meters, this one's still 0. Okay? Let me ask you this. What if I was evaluating it at 9 meters, at x equal 9 meters? Yeah, none of them would be 0. All the terms would be playing in that last segment of the beam. Make sense? Okay. And again, I don't want to bore you by punching all this in a calculator, but if you trust me, y at 8 meters should turn out to be negative 0.02079 meters. Let me ask you this. Let me take a pulse really quick. Do you guys like this method? I promise you, if you use it for a while, you will love this method, right? This is a wonderful, wonderful method to use. Did you have a question?
What does the negative sign mean in terms of which way the beam is deflecting?
Okay, so literally that's maybe the easiest thing in the world to, what does that negative sign mean? Literally what it means is the beam deflects downward, not upward, right? Where we're using the letter y to describe this, that's literally like y as a function of x. It's describing what that curve is of the beam, right? So pretty straightforward. Okay, any other questions before I want to show you one last little thing? Okay, let's go back up here. I said often what I like to do is start with the bending moment function, right? What if we didn't do that? I told you there's another method that we could use to kind of deal with this type of situation. And that is to start with, instead, the W function, okay? So let's try to construct this. Instead of starting with the M function, let's start with the W functions. So now we're up here, and let's again start at the left end of the beam. We started with a reaction that was at location A, right? Whatever that reaction is, times x minus a to the minus 1, okay? So W of x here is going to be equal to that load, 23 kilonewtons, times x minus 0, okay? Because again, this is x minus 0. There's no material to the left of that point. I'm literally just going to put this in here as x raised to the I'll tell you what, I'll go ahead and do it this way. I'll write it with full out, right? X minus 0, this raised to the minus 1. Minus, okay, and the form of that now is going to be that slope, which is 6 kilonewton per meter squared. And again, it's minus because it's pointing down, not up. 6 kilonewton per meter squared, multiplied by what? X minus a to the 1. X minus, what's a? 0. This to the first power. Then what? Okay. Then we have another triangular piece, right? 6 kilonewtons per meter squared. This one actually starts at a value, right? The a value where that one starts is 3 meters. So I'm going to do x minus 3 meters. And that's going to be to the first power. So I took care of that little triangular piece up there. Then I'm going to take care of the rectangular piece. So that's plus 18 kilonewtons per square meter. Excuse me, per meter. This will be x minus 3 meters, right? And this is going to be raised to the 0th power, right? What next? Last one we have to deal with is this concentrated moment, right? So for the concentrated moment, it has a value of, again, it's counterclockwise instead of clockwise, so minus 14 kilonewtons per meter, or excuse me, kilonewton meters. Sorry about that. Kilonewton meters. It happens at 8 meters, so this becomes x minus 8 meters. And this gets raised to what? To the negative 2. All right. What can I do with that function? I can integrate it. Okay. All right. Now when I integrate it, it gives me v of x, right? What does that first term become? 23 kilonewtons. What are my rules when I have a negative exponent? All you do is just increase the exponent by 1, right? So this just becomes x minus 0, right, raised to the 0. Okay, then what? Oh, so his question is, do you have to divide by EI? And the answer to that is, the EI gets introduced between m and the slope, between the bending moment and the slope. That's where the EI comes into this chain of integration. So at this point, we don't need EI yet. Okay, because we're just going from one load, a distributed load, to a shearing load that's happening in the beam. Okay, so there's that. What do we do for the next one? Same thing, right? We do x minus 0. This 1, what happens? Becomes 2, and then what? Divided by 2. Okay, the next term, plus 6 kilonewtons per square meter. This one's x minus 3 meters. That one gets raised to the, goes from 1 to 2. Okay. The next one there I have is plus 18 kilonewtons per meter, x minus 3 meters. This one is raised by 1, right? Which means I don't have to divide by anything. And the last one is 14 kilonewton meters, x minus 8 meters. This one gets raised by 1, so now it becomes x minus 8 meters to the minus 1. And if you're a good calculus student, what do you do at this point? You say, don't forget the plus c. I'll call it something else, and maybe call it C3, so I don't confuse it with the c's that we were doing earlier. Okay? Real quick, is there anything we can do to evaluate what C3 has to be? Okay? Question is, are there any spots where it's fairly easy for me to know what the shearing force is going to be in the beam? Yeah. At the ends, right? He says at the ends. Yes. Okay, so his question is, whenever you do this step of going from minus 2 to minus 1, do you have to actually multiply or divide by the new exponent, essentially is what he's probably getting at. And the answer is, ordinarily you'd think so, right? But what are our rules for our singularity cases? Don't divide by the new exponent. Don't add constants. Right? So even though it might seem like that's what we should do, no, we don't do that. Okay? And that's because these are special cases for these singularity cases. Okay? All right. So we were back on the topic of, are there any places where we already know the shear? And I would say is exactly right. At the end points where it's being supported, it's pretty easy for us to know what the shear is. And the easiest of those to kind of try to deal with is the left end, because that's where x equals 0. So if you look at x equals 0, we actually have a problem at that point. If it's actually equal to 0, what's the problem that happens? We end up with this x becoming 0. What does that give us? 0 raised to the 0. And what is that? That is, yeah, undefined or indeterminate, a couple of words that people use. That's a problem. What's not a problem, though? What if we don't make it equal to 0? We make it really close to 0, but still a little bit positive. Just to the right, barely, right? What would we call that in math terms? Limit as x approaches from the positive side, right? You might say 0 plus, something like that. All right, if it's 0 plus, now what does this term become? As long as what's in the brackets is not 0, anything raised to the 0, anything that is not 0 raised to the 0 is actually 1, right? So I'm going to say as long as x is just a little bit more than 0, then this term becomes 23 kilonewtons. Agree with that? Okay. What about all the other terms, right? The ones like this one right here that has a 0 in it, that one doesn't suffer from the problem of having 0 to the 0, right? So I can plug in 0 for that x, and this whole term becomes 0, right? What about the next one? Plug in 0 for this one. Right, because 0 is less than 3 meters, Macaulay function says that term becomes 0 when I'm evaluating it at 0. So that term becomes 0. Next one also becomes 0 because, again, 0 is less than 3 meters. This one also becomes 0 because 0 is less than 8 meters, right? So all my terms except that one right there are 0, I guess, and the C3. What should this function become at x equals 0, or x? Now we're saying it's barely to the positive from 0, right? What should the value be? 23 kilonewtons, because that's how much we have applied as a reaction force at the end. And there hasn't been enough length to where this distributed load has caused it to be any different, right? Having had all that discussion, what can I say about C3? Okay, careful. This at x equals 0 plus, right, x 0 plus, the whole thing should be 23 kilonewtons. We get the 23 kilonewtons from this term right here, right? So what happens with C3? Unnecessary, it is 0. Does that make sense? Okay. What's the next step? We have to integrate again, right? What's m of x? The first term becomes 23 kilonewtons. Now, because I'm at 0, I don't have to use my special rules of integration or anything like that. It just becomes x minus 0 raised to the 1. What about the next term? 6 kilonewtons per square meter, x minus 0. This is now going to become raised to the 3. This gets divided by 3. As a result of that, plus 6 kilonewtons per meter squared, x minus 3 meters. This raised again to the 3, right? I missed something on this last one, didn't I? Divide, I already had 2 down there. This goes to 3. This becomes 6. This one also becomes 6. Sorry about that. Right when I decided to start going faster, you know, make a little error. All right. Now what? Plus 18 kilonewtons per meter, x minus 3 meters. This is now going to go to 2. This becomes 2 in the denominator. Then we do minus 14 kilonewton meters, x minus 8 meters, goes from minus 1 to 0. Okay? And again, like all good calculus students, what do we have to do here? plus another constant. Is there anything we can do to figure out that constant? Okay. So one way to do this is to notice for this body, there can't be any bending moment at the supports. It runs out of like room to actually react a moment at the supports. And it doesn't have a concentrated moment reacted at the supports. So we know it's got to be 0 at the supports. So at x equals 0, 0 bending moment, right? So that means we plug 0 in for all the x's. That makes the first term what? 0. Next term, 0. Next term, 0. Next term, 0. Again, those two terms, they're 0 again because of the definition of the Macaulay function, right? Because 0 is less than 3. Okay? And then the last one, 0 is less than 8 as well, so that one's also 0. And the whole thing has to be equal to 0 because there's no bending moment at x equals 0. So that tells me C4 also has to be 0. Good? All right. Now let's look at something. What bending moment function did we just end up with? The same one as we got by starting with the bending moment function. So you might find it, you know, I would say if you have this table, let me say it this way. If you have this table, I can't think of very good reasons why you would generally start with the load function, because it's pretty much just as easy to start with the bending moment function because you have them all laid out for you what they should be. The only time I would say it might be helpful to start all the way back at the load function and integrate all the way through the whole thing is if for some reason you forgot all of these and you didn't have the table. And as long as you remember the essential rules of how do you integrate singularities and how do you generally integrate them just generally, then you could start with essentially just that information, start with W and go all the way through integrating everything. Does that seem to make sense? All right. Any last minute questions for this one? Yes. So his question is, should you always use 0 plus if you end up with a 0 to the 0? I would say, you know, always is always a tricky term. I can't think of a time where you would not be able to do that. So I would say I'm pretty close to saying, yes, you always do that. I wanted to hedge just a little bit because I haven't given that enough thought to try to think if there's some kind of weird exception that I could think of. C3 in this, you know, where I was, sorry, up here. Oh, no, I was down here. Where I had the C3 right here, it was because at x equals 0 or x 0 plus, right, just to the right of 0, I know that the shear force has to be 23 kilonewtons. And I won't prove that, but you get that off of a shear and bending moment diagram pretty much, right? So it has to be 23 kilonewtons. We notice that all the terms except for that one, right, are 0. And it has to turn out to be 23 kilonewtons, which tells me that C3 has to be 0. Because the 23 kilonewtons literally just comes from that first term. Yeah. If you're trying to do it at x equals 10, what's your question again? If you're 10, let's say 10 minus, right? You're just before you get to 10, then your shearing force at that point would be equal to, it'd actually be equal to -4, right? Because over on that side, you've now gone to where you're in the negative according to our sign convention as far as the shearing force in the beam. But yes, that's what you'd have at that location. Okay? All right. Any other questions or anything? All right, I'm going to shut that one down.